Hello everybody. Okay, in the previous video, we accidentally got integral of this form, integrate from 0 to pi over 2, and then log of tangent theta, d theta, is equals to 0. Okay, and in this video, okay, we want to investigate a very similar looking integral, okay, that is from 0 to pi over 4, okay, instead of pi over 2, and then the same integrand, okay, log of tangent theta, d theta, okay, and then we will denote this as I, okay, we want to calculate this one. So, we by observing that the tangent theta seems a little bit nasty here, so we will let u substitution, that is u is equal to tangent theta, okay, then in that case, theta will be arctangent of u, okay, and then we perform differentiations here. The theta will be equals to 1 plus u square du, okay, then we substitute everything into this integral, so this become, okay, when theta equals to 0, u will become 0, and then theta is pi over 4, u will become 1, okay, so this will become log of u, okay, and then the theta will become du over 1 plus u squared, okay. Now we notice that this guy is actually arctangent derivative, okay. Then we use integration by part, okay. So what we have will be log u times arctangent u, and then 0 to 1, and then minus 0 to 1, and then we differentiate log u, which is 1 over u, and then times arctangent u du, okay. Here we use by part, okay, we use by part. Now we have to evaluate this limit here. When u is equal to 1, this is 0, okay, this is 0, so it's okay. But the problem is that when u is equals to 0, okay, this limit seems a little bit funny, okay. So we have a look. Limit u tends to 0, log u arctangent u, okay. Actually, it is a type of zeros times infinity, okay. Now, in order to change it to a more manageable type, okay, we changed it, we flip the arctangent u into 1 over arctangent u, okay. Now, it will become type infinity over infinity, okay. Then in that situation, we can use L'Hospital rule. So the upper part and the lower part, we separately differentiate it, okay. So log u will become 1 over u, and then arctangent 1 over arctangent u will become minus 1 over arctangent square u, and then we use chain rule. Chain rule tells us that it will become 1 plus u squared. Okay, so we clean up these expressions. Okay, what we have will become limit u to 0, and then minus here. Okay, and then arctangent square u over u, and then times 1 plus u squared. Okay, since we know we input u equals to 0, this part will be 1, okay, and then here still 0 over 0, so we can split these two into two limits, okay, these two parts into two limits, okay, so it will become 1 plus u squared, and then times limit arctangent square u. Of course, this part will become 1, okay, and then for this part, okay, we go here. This is a type of 0 over 0, okay, so we use L'Hospital rules again, okay, it will become 2 arctangent u, and then times 1 plus u squared, and then here's 1, okay, beautiful. And then we plug in u is equal to 0, okay, which is 0, okay, which is 0. So we conclude that limit u tends to 0, log of u arctangent u is actually 0, okay, we will have this limit here, okay. So this go back to the integral, okay? This part will be vanished, okay? So we left as minus part of this integral, okay? So, okay, let's move to the new page, okay? So what we got here, I power over 4 log of tangent theta. Okay, in this case, we will conclude it will become 0 to 1 arctangent u over u and then du. Okay, so it seems that we have got no progress. Okay, we just turn one integral into another. Okay, now we know that the Maclaurin series of arctangent, okay, arctangent x, okay, is actually equals to sum, okay, sum, and then we start from k equals to 0, okay, and then minus 1 over k, 2k plus 1, and then x 2k plus 1, okay. We know that the radius of convergence of this guy is 1, okay, but in fact, okay, this infinite series is also valid for x equals to 1, okay, because you know this is a strictly decreasing function, okay, and then by alternating series tests, okay, we know that this will converge, okay, of course conditionally, okay. Then we make use of this series into this integral, okay? So I will become 0 to 1, and then we plug in here. Okay, so it will become k is equal to 0, and then minus 1 over k, and then 2k plus 1, and then x to the power of 2k, okay, and then dx, okay. Now, we know we can switch the summation sign and the integral sign, okay, so what we have will become this one, 2k plus 1 here, and integrate 0 to 1 x to the power of 2k dx, okay. Now, this integral is easy, okay. It's just, basically it's just x to the power of 2k plus 1 over 2k plus 1, and then from 0 to 1, and then we get it, which is just 2k plus 1. So in that case, we know this will be square, okay. However, this guy looks very interesting, okay. It is an alternating sum of all the odd integers, okay, of their square, okay. In fact, there's a symbols for this one, which is a capital G. Capital G is called the Catalan constant, okay. Okay, let me write down the definitions for this guy. Okay, we'll call it Catalan constants. Okay, I misspell it. It should be no n here. Okay, Catalan. Okay, Catalan's constant. Okay, so in that case, okay, we conclude that okay, this constant is very beautiful. Okay, it appears in various integrals. Okay, we will see in the future videos. Okay, and then so what we have today here is the 0 to the power of 4 log of tangent theta d theta is equals to this very beautiful mathematical constant, okay, G, big G. And interestingly, okay, previously our result, okay, when the interval is expand to the power of 2 instead of power of 4, we have the same integrand will be 0, okay, compare with this, okay. Okay, that's for today, okay, and I hope you guys enjoy this video, and we will see you very soon, okay, because we will make use of this result to derive another beautiful integral, okay. See you, bye bye.